Hello and welcome to the fourth lesson in space physics. Reminder that this is physics only, it's not in combined science. And today we're going to look at the Doppler effect and redshift. My name's Mr. Pratt, Director of Science. So for the lesson you're going to need a pen, paper or an exercise book. There's some quite important notes that you need to make, probably one side of A4. Unless you're needing to watch this video on your mobile phone, get it out of the way, get it on silent and avoid all the distractions that you can. Let's have a look what you can recall, and this is from the last lesson. We've got an image of Saturn there, 62 moons, lots of rings. I want you to explain which of the rings orbit Saturn the quickest. So I don't want you to just to say which ring it is, I want you to explain why that is. 1 minute. Okay, should we just finishing off? To answer this then, if you think about what you already know from the last lesson about the planets in the solar system and their orbits, we know that Mercury has got an orbit 80 odd days. It needs to go round with the greatest velocity, and that's because it's got the greatest gravitational force acting on it, because it's got the smallest circle of orbit. So the one closest to the surface is the one that will have to go the fastest. We're going to look at then the Doppler effect. We're going to explain what it is, what causes it. Then we're going to link that to the term redshift that you've probably heard of, and we're going to describe how it's observed. That then will lead into the next lesson where we're going to look at the evidence that we've got for Big Bang theory. So sound is a longitudinal wave. So if you look at the top bit of that diagram there, we've represented a longitudinal wave. So the areas where the lines are closest together are where we've got a compression, and the areas where the lines are furthest apart, we've got a rarefication. So the wavelength is marked there between two compressions, and I've marked it on there. But for the purpose of what we're going to look at next, explaining the Doppler effect, we're going to represent the sound wave just as a transverse wave. So the distance between the two compressions we've just marked as a peak to peak. If you increase the wavelength of a sound wave, the frequency decreases. That's because of this equation we've got here. If we've rearranged the wave equation, so v equals f times lambda, frequency then is the velocity divided by the wavelength. So if we make the wavelength greater, it will make the frequency less, and vice versa. If we make the wavelength less, it will make the frequency greater. So we've got a wavelength like that. We make it bigger by stretching it out, so we've got a bigger wavelength, and that means that we've got a smaller frequency. If we make the frequency of a sound wave smaller, we get a lower pitch, a smaller pitch, so a lower note. If we do the opposite, if we decrease the wavelength, so we go from a bigger wavelength down to a smaller wavelength, the wavelength is about halved in that diagram, the frequency will go up. If we've got a smaller wavelength, the waves will be more frequent, they'll be happening more often. So if we've halved the wavelength there, that will be, or have the effect of doubling the frequency. So we get a higher sound, higher note. Diagram here of a fire engine. Fire engine is travelling from B towards A. And as the object, in this case the object is a fire engine, as it moves towards A, it's driving into the wavefront, so it's squashing it, it's compressing it. So in front of the fire engine, the wavelength is decreased. If we decrease the wavelength, we increase the frequency, so you get a higher pitch. So at point A, the pitch will be higher. It'll be higher than it would normally be if the fire engine ring. But if we look at point B now, it's moving away from point B, so it's stretching, making the wavelength greater, so the wavelength is bigger behind the fire engine. If the wavelength is bigger, the frequency is smaller, so you get a lower pitch. So if you're in front of the fire engine, higher pitch. If you're behind the fire engine, lower pitch. You do need the fire engine to be going fairly quick. The speed of sound is about 330 meters per second in air. So you do need it to be going relatively quick. If it's going very, very slow, it's not an effect that you'd notice. And this is also true when we look at the Doppler effect with light shortly. So this effect of changing the wavelength of a wave because the object that's emitting the wave is moving, that's called the Doppler effect. It's more noticeable in sound, but it happens in all waves. To explain the change in the sound as the train moves towards and then away from the observer. I'm going to give you one minute. Time up. Let's think about when the train is moving towards the observer then. So it's moving pretty quick towards the observer. So it's squashing up that wave. So the wavelength is smaller in front of the train, bigger behind. So as the train is coming towards you, you end up with a smaller wavelength, which is a bigger frequency, higher pitch. And then as it moves away, you get the opposite. So that point where it goes from coming towards you to away from you, you get that sudden change in pitch. Let's move on to light waves then. Doppler effect can be applied to all waves. As long as you've got an object that's moving and it's emitting waves, you'll get the Doppler effect. With light though, it's not the pitch that changes, it's the colour. The colour of light is determined by its wavelength. So we've got a small wavelength on the left going up to a big wavelength on the right. So for light, the small wavelengths correspond to a violety purpley colour at that end of the visible spectrum, going all the way down to red with a bigger wavelength at the other end. If you go off the two ends, we've got ultraviolet, which is a smaller wavelength than 400 nanometers. That's 400 times 10 to the minus 9. And infrared is bigger than around about 750 nanometers. So if we change the wavelength, which can happen by the Doppler effect, it changes the colour. Now there's two ways that it can go. We can end up with a red shift where the wavelength has been made bigger because the wave is shifting towards the red end of the spectrum, or blue shift where the wave is made a smaller wavelength, so it's shifting to the blue side of the spectrum. And in cosmology, astrophysics, we'll be applying this to objects that are emitting a lot of light, like stars and galaxies, otherwise it'd be quite difficult to see them because we're normally observing things that are quite a large distance from us.
Everybody's heard the Doppler effect. But did you know that you need to take the Doppler effect into account if you want to communicate with a spacecraft? I've got here a Doppler ball. It's designed to illustrate the Doppler effect for sound. Of course, the Doppler effect works for all types of waves, electromagnetic waves as well as sound. But this is going to produce a sound with a constant frequency. It's the source of the sound, it's sitting here in the middle, and you can imagine the sound waves radiating out, getting further and further away, just as you would see ripples on a pond if you dropped a stone in the middle. If this source of sound stays constant, stays still here, then each distance from one wavefront to the next, to the next, to the next is going to be constant. We've got a constant frequency. But now imagine if the source of the sound is moving. If the waves are spreading out like this, and my source is moving as well, then if it moves in this direction, it's going to catch up with the waves in front of it. And the distance between one wavefront and the next is going to reduce. On the other hand, looking behind the source, the waves fronts are going to have a bigger distance between them. On this side, the wavelength is shorter and the frequency is higher. On this side, the wavelength is longer and the frequency is lower. Let's see if we can see that in action. I'm going to turn on the sound and now I'm going to spin it around. As this comes towards the microphone, you should hear the sound pitch go up, and as it comes away from the microphone, you should hear the sound go down in frequency, a lower note. Up and down as this ball goes away and towards the microphone. So there's the Doppler effect in action. So what's true for the Doppler ball is also true of satellites in their orbit around Earth. Sometimes they're coming towards the base station and sometimes they're coming away from it. As they approach the base station, the frequency of the waves that they're emitting is going to become shortened, the frequency is going to be increased. And as they're moving away from the base station, the frequency of the waves they're emitting is going to be stretched, the frequency is going to decrease. If you're going to communicate effectively with them, you've got to take that into account. The Doppler effect becomes even more interesting when we start to look at light and other electromagnetic radiation that reaches us from distant stars and indeed distant galaxies. Imagine that this wave here is some light that's reaching us from a distant star. You can see the wavelength of the wave here. We've gone from one peak to another peak. And this is what we would expect the frequency and the wavelength to be. But it's not. When we measure it, what we find is that the wavelength has become stretched. The frequency has decreased, and that's because the star is moving away from us. It's actually travelling further away, it's travelling away from us at a fast speed, and we've got the Doppler effect going on. The wavelength has increased quite significantly. In fact, it's shifted from the normal visible spectrum towards the red end of the spectrum. This is a phenomenon known as red shift. What's even more interesting is that we find a huge red shift when we start to look at distant galaxies. And what we've discovered is it's not just that they're moving away from us. In fact, the whole universe is expanding and causing this effect. We're really privileged today because we've been allowed to carry out this demonstration in the European Space Agency's test facility. Just take a look around. It's in this room that spacecraft can be tested and checked out before they go into space. It's designed to absorb every single radiation that hits the walls. As the waves hit the cones, they are absorbed. There are no echoes in this room whatsoever. Let's just hear it one more time.
Summarise then. As a galaxy moves towards us, the light gets squashed, so that means the wavelength is smaller, so it's getting more blue. There's us, galaxy moves towards us, squashes the wave and makes it bluer than we would expect. Most galaxies don't do that, but Andromeda, that is the nearest galaxy to us, is physically moving towards us, so it is slightly blue shifted. That's called blue shift. Moving towards us, squash the wave, smaller wavelength, blue shift. The more blue shift it is, the more the light has moved towards the blue end of the spectrum, the faster that it's moving, the bigger the effect. And the opposite's true. If the galaxy moves away from us, the light is stretched, making it appear more red. Wave's bigger, moving towards the red end of the spectrum, so we call that red shift. Amount of red shift tells us how fast it's moving. The bigger that red shift is, the faster that it's moving away from us. Question is now then, how do we know what colour a galaxy should be? Well, it's not quite as simple as that, because we're not looking at the colour of the whole galaxy, we're looking at something specific. So the nearest galaxy, apart from the Milky Way that we're in, is 2.5 million light years away, a huge distance, and that's a galaxy called Andromeda that it's estimated has got roughly double the number of stars in it that the Milky Way galaxy has, so it's big. That's what it looks like through a telescope. You can find it in the night sky, and it is visible all year round in the UK. If you find the constellation Cassiopeia, which looks a bit like a wonky W, and you'll see it all the time, it's quite high in the sky. If you can find that, which is relatively easy, and then look below it, slightly on the right hand side of it, you'll see there's a fuzzy blob. You do need quite a dark sky to see it, but it is just about visible to the naked eye. It looks more of a fuzzy blob if you get a pair of binoculars or a telescope. So that's Andromeda. So that's how many miles it is. I'm not going to read that number out. And that's the closest galaxy by quite a long way. Furthest galaxies that we know of, 13,000 times further away from that. So if you can find Andromeda, it is the most distant object that you can see with your naked eye from Earth. So let's have a look what astronomers actually observe. You get a telescope, but when you've got your telescope, you put in a bit of equipment on the end that analyses the spectrum. So you'll see something like this. If you imagine just getting the light from a bulb and putting it through a prism, and sometimes you'll just get it from a bit of glass, you'll get effectively a rainbow, a spectrum. So that spectrum is all the light spread out from violet all the way down to red. So you'll see that from all stars. But it has dark lines on it. The dark lines are called absorption lines, and they're caused by the gases in the outer atmosphere of the star absorb specific colours, and those black lines tell us about the elements that are in there. So the lines you can see there, hydrogen, helium, so you'll get those lines whenever we look at stars. What happens though is that those lines can be moved either to the right or to the left if we look at it there, and that the one that we've got there is red shifted. So those dark absorption lines have moved towards the red end of the spectrum. So that galaxy that we're looking at there is red shifted, which means it's moving away from us. If we get those lines moving across to the blue side of the spectrum, then it's blue shifted, and that's what you'd see for Andromeda. You'd see it moving towards us and squashing the wavelength up as it does so. Exam question then, 3 marks, so I'm going to give you 3 minutes. So this is similar to what you saw in the video clip with a speaker being rotated. I'm going to give you three minutes in total. It's 1 minute gone. Okay, so when you're explaining what the Doppler effect is, it's 2 marks. So you need to mention, first of all, that it affects all waves. So it's an effect on all waves where their wavelength can be decreased or increased because of their movement either towards or away from an observer. And then we need to talk about what redshift is and what it does to the size of redshift, what it tells you about distant galaxies. I'll stick you onto the mark scheme. If you self-assess it straight from the mark scheme. You'll notice there on part A that it does talk about observer relative to each other. So if you've got a fire engine that's got its siren on and it's stationary at some lights, but you're moving really quick past it, you'll also notice the Doppler effect, that shift in the pitch as you go past it. We'll do a little bit more about the last point on part B there in the last lesson on the space physics topic. So the bigger the red shift, the further the galaxy is from Earth. This is evidence that leads to the theory of the Big Bang. So we'll be looking at that in a lot more detail in the last lesson. Another question for you again. I'm just going to give you 2 minutes for this one. This is specifically about a binary star system. So we've got 2 stars there, star A and star B, that are rotating in a circle around a fixed point. There are quite a lot of binary stars out there, probably more than there are individual stars. 1 minute left. The diagram of star A and star B can potentially be a bit confusing there. If you were looking at those stars as they are on the picture, you wouldn't see any red or blue shift at all. You wouldn't see any evidence of the Doppler effect, and that's because they're going around in a circle. You'd have to be looking at them edge on, so that one of them is going towards you and one of them is going away from you at any point. So not from above like it is there, but edge on. When you're answering this question, we're talking about 3 marks. It's an explain how, so we need some physics in there. But if you start at the absorption lines that we've got there, so we've got the sun, and we assume the sun is not moving towards us or away from us, so we've got something to compare it to. So star A then, the 2 lines that I think are probably helium lines there, the 2 lines there from star A have been shifted to the right. Now if we look at the bottom, being shifted to the right means that their wavelength has increased. Star B then, the lines have shifted to the left, which means that those lines, the light has been, wavelength has been decreased. That means then, if the wavelength is decreased for star B, it must have been moving towards us, squashing the wavelength up, and star A must have been moving away from us, therefore stretching the wavelength. I'll give you the mark scheme and then you can mark it. There is 2 marks there for, well, 1 mark for saying star A is moving away and 1 mark for saying star B is moving towards. The other mark is just explaining that it's one of them's red shifted or blue shifted. I'll leave you with the summary then. It's important that you got to grips with this because you're going to need it to apply to Big Bang Theory in the final lesson of the space physics topic. So we've got a little explanation of how it affects sound and what the Doppler effect does, and then we've got the spectral lines on there and just a little bit about the binary star, just in case you come up with a question like that. See you next time for the last lesson on space physics.